So let's open. Everybody has the write-up? Me lab.
No, I have it. It's right here.
What?
Sorry, I printed it and I didn't put it.
But it was not put online?
Yeah, it's online.
It's online, so you can see it there.
Look at it online.
Then you can also look at the.
Is it in the drive link you sent us?
No, it is on the website.
Oh, it's on the website.
Sorry, yeah.
Somebody took my Born in Hoffman. Somebody borrowed Born in Hoffman. Okay, it's fine. No big deal. So I'll read it from this way. Thank you. Somebody borrowed the Born in Hoffman book, I think. Anyways, there's two classical textbooks you want to have. This one cost $12, I think, because it was published out on Dover sells, and it's called Light Scattering by Small Particle, written by a very famous optics guy named Van der Hulst from the Netherlands. Excellent book. You should have it. For $12, it's you're not going to bankrupt yourself. Should be on any aspiring optical oceanographer's shelf. It's called Light Scattering by Small Particles.
I was getting the author's name.
Van der Hulst. Hulst. And the other book, which I showed you the first day, maybe you have a copy of it over there, Colin, as well. It's Light Scattering by Small Particle from Born in Hoffman, 1983. And there are PDF copies of that circulating. Yeah. Anyways, these are kind of the Bibles of scattering, both with examples, there's a lot about polarization in them, a lot of good examples, a lot of good summaries of the old literature, the Me solution, all that is there. You will need a computer with MATLAB on. You can work together. And here is what we're doing now. And the code you're going to be using is based on a code that's in the Born in Hoffman in Fortran, and I translated it to MATLAB when I just became a postdoc in optical oceanography, and have used it ever since and distributed. But there's you do Me codes on the web. There's gazillion codes. Many people have either translated, copied, made code available for people to use. And similarly for non-spherical particle or for concentric spheres, etc., there are many codes on the web. So what are the input to a Me code? So a Me code calculate the scattering and absorption property of a homogeneous sphere. So what do you need to tell it? You need to tell it the wavelength of light interacting with the particle in the medium. So
cytoplasm soup.
This is the wavelength. Well, one thing at a time. So we start with wavelength. And do you think that the wavelength in the medium is the same as the wavelength in air? It's not. Anybody knows how they're related? So if I know the wavelength in air, how do I compute the wavelength in water?
Multiply by n.
You have to multiply by n. So how will I remember? This is the way I remember. What is preserved is energy, when you go from one medium to another. And energy is h nu. So these are preserved. So frequency is the same. And frequency has units of 1 over time. How do I get with wavelength and speed to 1 over time? So nu equal c over lambda. Okay, so I have c1 over lambda 1 here. c2 over lambda 2 here. The h's I can cancel. And lambda 1, sorry, C1 over lambda 1, C2 over lambda 2. These have to be equal to conserve energy. So now I'm going to ask, what I'm asking is, I'm going to call one water, because that's the one I want. And I'm going to call this guy air. So now I'm going to invert it, and I'm going to say that my wavelength in water equals to my wavelength in air times the velocity in water divided by the velocity in air. And the velocity in water divided by the velocity in air equal to the inverse of the index of refraction. So n in air relative to n in water. So now I'm putting that in. I get the wavelength in water is n air, index of refraction in air divided by that of water. And water relative to air is about 1.34. So this is equal to lambda air divided by 1.34. So the wavelength gets shorter in water. And since scattering is due to interaction of the wavelength with the size of the particle, I really need to know the wavelength in the medium. But all the wavelengths we've been talking about and the wavelength reported by your instrument are always in air. They're always in air. So when you do calculations, you have to correct for the actual wavelength in the water. So frequency is conserved, but not wavelength when you go from one medium to another. Okay? So that's one thing I have to keep track of. I need to know what wavelength in, because that's the size of the wavelength relative to the size of the particle is what matters for scattering. And those of you who've done chemistry, how many of you, you all took chemistry. When people would do spectroscopy in chemistry, how many of here did some spectroscopy in chemistry classes? Anybody? Kinda? Do you know how you report light usually in chemistry? Either frequency or wave number, but not wavelength. So the reciprocal. Why is that? Because the resonances for absorption, the things that Colin showed you, actually depend on frequency, on quanta of energy for absorption. So people that are focused on absorption, chemists focused on absorption, very often don't do things in wavelength when you look at their literature. It's all in frequency space or wave number space. People doing scattering, it's all in wavelength space. So this is one thing we want to know. Another thing, index of refraction of the medium that you're in, and since we do everything relative to air, and we're assuming also it's non-absorbing. There are codes out there for an absorbing medium. We're not going to assume it here. So index of refraction relative to air. And so often when you're going and looking on the literature, you want to know what's the index of refraction of quartz. You're going to get something like 1.54. This is relative to air, sorry. So quartz relative to air will be something like this. But what matters when light interacts with a particle in the water is the index of refraction relative to the medium in which the particle is embedded. So the actual index of refraction will be this divided by that in the medium. So this is, if this is relative to air and this is relative to air, it's the same as the index of refraction of that material relative to water. Okay, so you're doing them each relative, if you wanted to, relative to air, or directly, what is it relative to water? So you want to know the index of refraction of the material you're putting in relative to the medium it's in. So don't get afraid if you see that somebody says quartz 1.2 and another said quartz 1.54. It's the same quartz, just referenced to a different medium. This is why you scatter differently. We saw that material in the, that rod of quartz we put in. It scattered a lot in water and almost was invisible in that oil because the oil had the same index of refraction. So what matters is how different you are in speed relative to the medium in which you are. So you want to know that, and you want to know the size of the particle. And because the inputs themselves are going to be ratios, we're doing this in the same unit as we're doing the units of the wavelength. So units are important. You do the wavelength in micron, size in micron. Wavelength in nanometer, size in nanometers. Just keep track of that, because this is how we make big mistakes. And then again, the imaginary index of refraction of the material, if it's a phytoplankton, it's going to be the absorption if it was not quantized in. So if all the fluid has that absorption, it's not just one small particle, times I think it's not charging. That's why I get, now it's charging. And so it's times lambda divided by 4 pi. That's my n prime. And the solution is given in terms of cross-section or efficiency factor, not in terms of what you want. So you have to translate it to something that you want to get. If you want the attenuation of one particle, you have to multiply that cross-section by that efficiency factor by the cross-sectional area of the sphere to get the optical cross-section, which is for example, if the attenuation of a single sphere in a meter cube, and then you multiply by the number of cells that you have in that meter cube to get the total absorption or attenuation. So this is what we're going to go through. So we said, if you want to know the beam attenuation, you want to have the cross-section times the number. But if your output is an efficiency factor, you have to calculate this by multiplying Q by pi r squared, or cross-sectional area. And you know that. So in the end of the document you have, if you open the last page of the document you have, there's a whole bunch of theoretical solutions done. And often they work really, really well. Particularly the one, so Rayleigh for very small work well, the Rayleigh-Gans regime work well for kind of intermediate. Anomalous diffraction is the one that before we had computers, a lot of people used for phytoplankton. They use this one, and we're going to see how different it is. And the definition of each of these things with respect to what we wrote here are at the top of the page here. So index of refraction, size parameter, this x, phase lag parameter, optical thickness, and this beta parameter, all are given. It's all stuff you can calculate once you have the index of refraction, relative to the medium, and the size parameter, which is based on the wavelength and diameter. Okay, so far? Riley, have you done it before? Okay. Okay. So we're going to start with a simple example. Let's assume this phytoplankton. I want you to go to the last page and check which approximation could it do. So you have to calculate for it. The size parameter, you have to calculate for it. What else do we have there in the approximations? We have to calculate, if we go all the way to the back, the size parameter, because I'm checking for that, and we want to know the index of refraction, how far it is from 1, because that's what I often look at. So we want, so what is our size parameter for this phytoplankton? What goes into a size parameter? Pi times d times lambda in the medium. Okay, what's my lambda in the medium? It's 440 in air. So lambda medium equal 440 divided by 1.34. What is that equal to? What's the wavelength in the water?
440.
Divide by 1.34.
328.
328. So it's UV, and why do we call it visible? So this is in water. The diameter, so this is in nanometer, or 3.28 micron. Is it correct? No, 0.328. 0.328 micron. And I need to know diameter. My diameter is 2 micron. And then I have a pi because it's a sphere. So x equal 6 divided by 0.3, let's say. So something like 18, 20, something like this. How does it, is it significantly bigger than 1? Yeah. So this is significantly bigger than 1. So Rayleigh regime is not going to give me a good solution for this phytoplankton. Let's look next. The index of diffraction, is it close to 1 or far away from 1? It's close to 1. I'm not very different from my medium. So my M is not very big compared to 1, or M minus 1 is significantly smaller than 1. What regime does that? No, Rayleigh-Gans is still, there's still not, you have this rho parameter. Do you want to calculate what this rho parameter is? What is rho? Rho is n to the minus 1 times x. So x is about, we said is about 20. N to the minus 1 is about 0.05. This times this is about 1.
Missing a factor of 2.
Oh, sorry, 2. So it's about 2. Is 2 very small compared to 1?
No.
So we're not Rayleigh-Gans. So anomalous diffraction, exactly. Mass diffraction, and we know a lot of people have used it too for phytoplankton, but yes, we're in anomalous diffraction. So now let's do this. What is the attenuation, scattering, and absorption per cell based on that approximation? So I have a little code I wrote just for that, so we don't have to think about it. So let's open MATLAB, all of us. Yes.
Can you briefly describe why we chose anomalous diffraction again?
Because from all of your approximation in the back, it's the only one that you're obeying what it assumes. So what we have, these are the assumptions. Their size parameter is bigger than 1 significantly, yet their index of diffraction is quite close to their medium. So minus 1, it looks like it's close to 1. That's why we chose it. I have to find the code. Me code, here it is. So I have one code that's called ad.m, anomalous diffraction.m. Function, so this is what, it's a function. You give it your diameter, your wavelength, your real part of the index of diffraction, the imaginary part of the index of diffraction, and it calculates for you what's your, based on exactly what you have on your page, what the attenuation efficiency factor is, what your absorption efficiency factor is, and what your scattering efficiency factor is. And lambda has to be in the medium, because I'm not correcting for that here. And NP is N prime. That's what I have there. Okay? So how do you call that function? You basically copy this part into your, and you have to change directory. So if you'll ask me change folder, I'm changing folder, and then you tell me it cannot execute it because it's a, which is totally fine. And then I have to open my MATLAB. my command window. Now I'm in our command window. And so what is my diameter based on the question? What's the diameter of our cell? 2 micron. So it's in micron. I have to be careful. My wavelength, we said in micron, is 0.328. 0.328. My index of refraction is 1.05, the real part, and the imaginary part, 0.5, is 0.01. Is that consistent with everybody? Can you see this? Is it too small?
Could you explain the imaginary part of the index? Of
Yes. So the imaginary part is a representation of absorption.
Okay.
Now, because there's a complex part of it, so you can imagine what happens when, if you do, you know what e to the I represents? E to the I x. This is, it's just complex notation, cosine x plus I sine x. So these are oscillation. Now, if instead of this I add e to the I index of refraction, the imaginary part will cause a decay, because I times I is -1, and that's providing you the decay rate of light within a cell.
Okay.
So the imaginary part is absorption, which is the decay of light, while the oscillations are the scattering. That's the real part of the index of refraction.
Okay.
It's just compact notation that makes everybody else miserable, because you're not putting in absorption. Instead, you're putting it something that's proportional to it. But that for a mathematician is much easier to solve.
And that shows up.
It shows up here.
As a way to represent
Exactly.
the index of refraction.
Exactly.
With
With an absorption. And you can back it out, as I showed you in this paper from Bricot and Morel. If you go back to that paper, they show you how you back it up from your absorption spectra.
Wow.
You take an absorption spectra and turn it into a spectrum of n prime, of the imaginary part of the index of refraction. Okay? So if you want to get deep into it, by all means do. I didn't want all of us to have to go through all the derivation. But it's there, it's in those papers, it's not too hard.
Cool.
If you have absorption, you can back out, and you know the number of particles you have, you can back out what the imaginary part of the index of refraction should be. And actually, we'll do a little example of that with the code. So, okay, anomalous diffraction, size 2 micron, wavelength 0.328 micron. They have to be in the same units. Index of refraction, real part 1.05, imaginary part 0.01. Press enter. These are I'm getting QA, QC. I don't know why again QA. That's a typo. Same value. And QB by difference. Okay, so how do from these I get my cross sections? I simply multiply the cross section of the particle, pi d squared times q. That gives me the attenuation of 1 particle per meter cube, if I multiply this by QC. So C of 1 particle per meter cube equal pi d squared, and I'm doing everything in units of meters. So this is 2 times 10 to the minus 6 meters pi d squared. I have to square it. QC is 1.55. I have pi. So 1.5, can somebody do it? Pi times 1.55 times 2 10 to the minus 6 meters squared. What do you get? And it's going to be in units of meters squared. 9.73 times 10 to the minus 6 meters squared. You sure? Because this, you should square it. This has to be the 2 square, so it's 4 times 10 to the minus 12. So it's maybe 1.95 times 10 to the minus 11. Okay. That's really small. But this is the attenuation if I had 1 particle per meter cube. What's the concentration of particles that I have? How many?
5 times 10 to the 4 plankton per milliliter.
Plankton per milliliter. Is this a reasonable concentration in the ocean? Do you have kind of a understanding of how many do you expect? How many bacteria per ml, upper ocean? What? How many?
I only know liter.
How many bacteria per liter?
Not a trillion. The other one, billion.
10 to the 9th.
Yeah.
So per milliliter, 10 to the 6.
Okay.
Exactly. You expect
Not a
about
trillion. It's a billion.
Faster, faster.
10 to the 6 bacteria per milliliter. Excellent.
And then plankton's the next one.
Plankton are bigger, so there'll be less of them.
So it's
It's about 10 to the 4th, 10 to the 5th, depending per milliliter. Just if you had to kind of guess a number. So this is a number that's consistent with what we might expect to find. Okay? So it's an order of magnitude of the right kind. So these are plankton per ml, but I want plankton per meter cubed. So if this is per ml, by how much do I need to multiply to get per meter cubed?
what's the density?
I have 5 10 to the 4th plankton per meter per ml.
Yeah.
How many do I have per meter cubed?
Wouldn't it-
1,000, it's in liters. Another 1,000 is in meter cubes, because there's 1,000 liters per meter cubed. So 10 to the 6. So I have 5 times 10 to the 10 plankton per plankton per meter cubed. Okay? So far so good? So now per meter cubed, so meter to the minus 3. So now I multiply this by this, and this will give me the beam attenuation I should expect in my culture. Okay? So what is the beam attenuation due to this phytoplankton? This is going to, what? 0.97. What are the units? This was in meters square. This is meter to the per meter, or meter to the minus 3, or divided by meter cubed. Meter to the minus 1. Exactly what the AC9 gives us. Yes. So you can get a sense just based on phytoplankton value concentration in your culture, values from the literature about how much they scatter, or put it into here because they know your size, and derive what you'd expect to see as beam attenuation. And then even decide, okay, based on this, I know what path length I should use, without ever putting your feet in the ocean. And if I want to do absorption, I do exactly the same exercise, exactly the same, but substitute for QC, QA. And this is going to give me what the absorption coefficient in here is. And it's about a factor of 4 less than this, so it's probably something like 0.25. My absorption of that, something like this, people got? Yes? So it's the same as before, divide by 1.55 and multiply by 0.3898. What do you get here? Something reasonable?
I'm making comments.
Oh, okay. What? But you see, it's not that hard to come up with an estimate of what, if I knew how many cells I have, what do I expect to measure optically for them? And stop me anytime for any question, anything.
Where did this equation come from?
This one?
That one.
This one? This is the efficiency factor, which is the optical cross-section per geometric cross-section of your sphere. I multiply it by the geometric cross-section, I get the optical cross-section. And the optical cross-section, I told you before and also today, is if it's the attenuation cross-section, it's the attenuation for 1 particle per meter cubed. And now I multiply it by the concentration of particle per meter cubed, and I get the attenuation for the whole suspension. And that is in units of per meter.
Geometric cross-section is something that's familiar, right?
It's a sphere.
It's like-
It's just pi d squared.
Okay.
It's,
But
this
optical cross-section
is what you're getting this to give you.
attenuation of 1 particle per
Meter cubed. That's the way I look at it, yes.
Okay.
If you had 1 particle per meter cubed, that's going to be its value.
1 particle and
Yeah.
all the light, and that's
Exactly.
that's the
And when you and the Q is the ratio of what's my attenuation cross-section to my
Right.
particle cross-section. That's the sufficiency factor.
and we're getting stuff like 1.5. It's
For the efficient, so it's almost 2. Geometric optics, we're going to get to 2 for this one. If they were really, really big, you can assume it's 2. You don't even have to measure it or run a code.
it's geometric to optic.
It's optics to geometric.
Optic to geometric.
Yeah. Yes, Juliana. How much was it? 0.24. Gee, almost. My math in my head is not as good as it used to be.
That's pretty good.
Andrea, is it okay? Adam? Does it make sense? If you have a question, ask. I don't want to lose you. So please ask. Please ask. Okay, so this we said is an approximation. What we got here is an approximation. So let's run the full solution to see how bad the approximation is.
Can we pause? What-
Yes.
What are these equations?
These?
Is that a dumb question?
With this one? This is beam attenuation of the particle in my suspension. This is the absorption by the particle in my suspension. And they were calculated by, I'm taking this, this is equal to Q, my efficiency factor, times the geometric cross section, pi d squared over 4. I should have divided by 4. Emmanuel, you forgot your geometry. Okay, so divide by 4. This is going to be 0.25 or 24, and this is going to be 0.006 inverse meter. Sorry. Q times cross section times the number of particles per meter square. The meter cube, sorry. So this is number per meter cubed. This has units of meter square. This has no units, and we end up with inverse meters.
Thank you. I would just need another.
Thank you for telling me, otherwise I would not have found my... Nobody told me my cross-section was completely overestimated. What, Olivier? Tell me.
Nothing, just having a moment.
Okay, but can you see from your corner? I would not ever be able to see in that angle. Yes, Lydia. AP is exactly the same, just a QA instead of a QC. And for scattering, it's QB instead of QA. Yes.
And the only things you need to know to estimate this are the index of refraction of the medium and the average size of the particles
And I need to know their index of refraction relative to the medium and the wavelength.
and the wavelength.
And the wavelength. Yeah, that's all I need to know. So far, so clear?
Is there any word for M other than index of refraction relative to medium? No, that's the best term for it. I could use a fancy word like squaw.
Maybe you should make one.
Okay. It's squaw. That's the new word.
Sounds great.
All right.
So what's the next question? Is now we're going to do the same with the full code? That's the next thing we're doing. So you open the full code. You'll have, it's called call BHME. So BHME is Born and Hoffman me code. So call BH.m. Okay? If you do call bh.m, you'll see that it has a bunch of questions it's going to ask you, and we're going to put them in, and then at the end it's going to generate for us a whole bunch of things, some of which are the volume scattering function, but they're going to come down below. And so let's run this code, and you can run it straight from here by running it at the top there. It's asking me, what is your real refractive index of surrounding medium? Since I'm doing everything in water, I'm going to call it 1, because I'm going to already do it relative to water. I'm going to put 1. 1 is my real. No, it's, of surrounding medium, it's 1. Real refractive index of the sphere, so now it's 1.05. Okay? That's with respect to the water. If we did it in air, I would put the medium 1.34, and here I'll have to put like 1.4 something. All it does in the software is calculate the ratio. So it's with respect to that medium. Next, what's the imaginary refractive index of the sphere? We said 0.01. So this is the full me code, meaning it's going to calculate a lot of elements and sum them up after it decided it counted enough elements for this sphere. So here is, it spits back to me, your real refractive index relative to the medium is 1.05 plus 0.01i. Good. And you can make it do many other things. Radius of the sphere. So radius is 1, because we did diameter before. 2. Radius is 1. Enter. We're doing it in micron. We could do it in nanometer, and then it would be 1,000. Let's do it in nanometer, just so you see it's the same. Wavelength, relative same as unit as the radius in the medium. So we said, so it's going to be, in our case, this was in micron, the way I write it, but now I do it in nanometer. So in nanometer, we said we were at 440 nanometer. So it's going to be 440 times, divide by 1.34 or times 0.65. It's whichever way we want to write it, because I'm dividing by the index of refraction. So wavelength in the medium. It's shorter in water than it is in air. Enter. The next is, how many angles do I want? Just put something like 181. That doesn't matter, we're not going to use it now. It's just the discretization of the VSF. How many angles do you get? It doesn't change anything in your solution. Enter. Output file. Whatever, test.dat. Or anything else you want to call it. Done. You can see, so now I have to open my test.dat. Here it is. My .dat opens immediately. So I get QC, QB, QA, and QBB. My QC 1.63. What did I have before? QC, I get 1.55. This I could do by hand, but with a fancy computer, I get 1.63. Not very far. My approximation is not too bad. My QA, 0.426. QA is 0.426. How was it before in my approximation? What was the approximation? QA. Anybody remember?
0.3898.
3898. 3898 was 39. So about 8% difference. That was my QA for the anomalous diffraction approximation. Not too bad. And then I get the VS. On top of it, I get the phase function. So I can plot what the phase function look like if I wanted to. How is the scattering? So if you want to do it, you can do it in Excel. You can do it any way you want. But one way I can do data, text to column. Next. I'm going to say it's space delimited. I'm just doing it in Excel because I'm too lazy to do it in MATLAB. Okay, here are my phase function. I got it every half a degree because I said 181 for 90 degrees. Let's do the first 90 because somehow we can move it. And on purpose doing it in Excel because this way you can see exactly what happens. There's no miracle, there's no... You get to see everything. Okay, so I have the angles on the left. I have my phase function on the right. For this phytoplankton, it's very narrowly distributed. I didn't give it any width for the size distribution. Just particle. Insert. Where is my chart? It's going to be X, Y, scatter. Yes! It's forward picked. And now if I want to do it, if I do log-log, let's try and do it log-log. Because we're going to see so much more on the log-log. Everything looks good on a log-log plot. How do I do that? It should be something properties. Format axis. I want logarithmic scale. Yes. Yes. And all these, you know why they're formed, all these? Because of the wave bouncing back and forth within the particle. So you have the wave going through the particle, the stuff diffracting, and this is bouncing. And if you have a wider size distribution, you're going to lose all of these oscillation. You lose them as you make a wider size distribution. And we will make a size distribution, promised. So far, so clear? We're all on the same page? We have an approximation. It doesn't give us VSF, but it gives us beam attenuation, absorption, and scattering for something like phytoplankton. It's not very different from its environment, but big enough relative to the wavelength. We can get the same, very similar solution running the full me code that also gives me the VSF. And we can take a break. 15 minutes?
So
Super.
this phase function is like what we saw when...
The list. So the list measures this. By the way, the list measures this.
Okay, so what are we plotting on the y? Is that just scattered?
So this is phase function is the normalized VSF. So if you multiply this by QB, that's going to be the VSF of a single particle per meter cube, which is what you want to get from this instrument over there in the first 21 degrees. 15 guys, go shake yourself, shake your booties, get coffee, do all the stuff you need to get done. Come back at, I don't know, 5 minutes before 3. And we'll play more together.